Welcome everyone to the second session. So the second session is on learning theory. It's hard. I mean, it's a very disparate topic. I mean, there is theory, learning. It's essentially all the results that you have on all the fields all the talks that you have, you're going to attend is learning theory. I mean, if you have learning theory of regularization, it's theory of regularization. If you have theory of ensemble methods, it's theory of ensemble methods. So almost every talk that you have has a learning theory component. That's basically that you can. So what is learning theory? So that's the first question you should ask. So learning theory is not just math. I mean, if you have math, it does not make it theory. Okay. So that's the first thing. So a theory is something which, if you must have a theorem, like it says that under these and these conditions on the problem, under these and these conditions on the algorithm, this is going to be the result that I'm going to get. So that's a typical learning theory result. So a typical positive learning theory result would be something like this. It would say for some type of ML problem, say classification, under some assumptions on the data, for example, you can always get a weak classifier with 0.5 plus gamma accuracy. That's kind of an assumption. And a particular algorithm will give the right answer. So the AdaBoost will give me the right answer, meaning the 100% accuracy with the number of samples and A amount of samples and B amount of computation. So this would be a typical learning theory result. I mean, just because you have a couple of equations does not make it a valid theory. So you have to make the assumptions under which. So how is learning theory different from any kind of, say, statistical, any kind of theory? So it's essentially, it comes from the assumptions on the problem. So the assumptions are what actually make theory even feasible. If you want to make no assumptions on any kind of the model or the data, you will generally not be able to prove anything. So for example, in AdaBoost, if you didn't assume that there was a weak learner at every iteration, you could not have proved anything. So you could not have, you would have just gotten stuck with 1 minus 4 gamma squared, which is 1. The error stays constant. That's not really an interesting thing. You want to say that the error goes to 0. That's the interesting result. So you have to make assumptions. So that is essentially one important, and you say that under these assumptions, I can make concrete progress. Or there is another kind of result, which is a negative learning theory, negative result, which is saying that you have this kind of problem, this kind of assumptions, there exists no algorithm which can get you the right answer. So these are the other, this is a negative learning theory result. And these are also very useful. And these are not the only type. I mean, it's not all algorithm related. So both these are kind of the algorithm centric, in the sense that there is an algorithm and saying that under certain conditions, this algorithm is going to give me the right answer. But it need not be the case. I mean, there are cases which are theorems which don't really say anything about the algorithm, but just give some intuition. But they are difficult to categorize. So they are, but these are the easy to categorize things, where you have an algorithm and you have it operating on some kind of problem, and you say that if you apply this algorithm with this data satisfying these kind of conditions, then this algorithm will succeed. So ideally, those are the kind of results to aim for. So those are results which will immediately interest people. You can have other kinds of theoretical results also, but they will not excite people as much. So theory that leads to new algorithms is always the best kind of theory, in my opinion. Of course, there will be differing opinions, but that's my opinion of things. Okay. So the negative learning theory results are also very useful, and they are in fact what started off the entire field of learning theory, saying that, well, these problems are impossible to learn. However much data you give me, however much computation you give me, it's impossible to learn. So those kind of results are also important, because you need to know the limitations of what's possible. I mean, it's, for example, if you are, I'm assuming you're all computer science students, in which case, if you know a problem is NP-hard, don't spend too much time on getting the exact answer. I mean, you know it's NP-hard, why bother? I mean, you just settle for, either change the problem or settle for something approximate. You change the parameters of success. You say, oh, I'm not going to define success by getting the exact answer. I'm going to define success by getting an approximate answer. Or I'm going to change the problem so that it is no longer an NP-hard problem. So it is important to also be aware of the limitations of a setting, and that's where the negative learning theory results are useful. Okay, so I'm going to have two parts here. One is the first part is I've labeled it the theory of the learnable, because this is the title of a famous paper in 1989 by Leslie G. Valiant. He's the Turing Award winner. I think 2014, I'm not sure. This year, I'm not sure. So as many of you might know, Turing Award is the Nobel Prize for computer science, and a theory of the learnable was essentially the learning theory was what Leslie Valiant was given Turing Award for. So it's the highest achievement in computer science, and it's a very elegant theory. So that's why I am by no means saying that I'm going to cover that paper. It's not possible, but still, it's a very evocative title, and that's what I'm going to call this. So the first part is the theory of the learnable. So what do I mean by that? Okay. So as I said, right, so you have to make the assumptions and the algorithm and the parameters of success clear. Only then you can say what. So I'll give some examples. Okay. So now the assumption is that so your data is drawn IID from. So I'll stick to classification throughout. So it's binary classification. That's the setting. I mean, obviously there are too many settings to worry about. I'm not going to be able to cover all of that. But the classic learning theory results are always mostly on binary classification. So that's actually an industry of its own. If you have some result on a binary classification, how do you extend to multi-class? How do you extend to structured prediction? How do you extend to regression and so on? So there are many, many machine learning problems, and extending theories which are already proven in, so that this is what, for example, say some big shot, say Valiant or Robert Shapiro would write a result on binary classification. They would focus the entire thing, and then they would result in the future work. This can be extended to multi-class classification and regression. And that's basically them saying that we are not interested in doing that. If you want, you can do it. So that's basically what, and that's an industry of its own, and that's valid. But mostly, if you have solved something for binary classification, you have mostly solved it for other things also. So you have to make modifications, but the intuition, the core intuition, remains the same. Right? So that's what we'll be doing. So what will make the assumptions and the parameters of success clear. Okay? So here is an example. Okay? So you have, let's say, for now, you'll imagine that all data, your x and y, the x is basically sitting in an R2 plane. It's a two-dimensional plane, so it's a two-dimensional vectors. So the feature is a two-dimensional thing. So that's the thing. So you assume that, say, data drawn IID from some unknown distribution. And you know that all positive data lie inside some rectangle, and all negative data lie outside it. So you don't know this, but you don't know what rectangle, but you do know that all positive data is going to lie in some rectangle, and all negative data is going to lie outside it. That's what, say, this is the truth. Obviously, you never know this. You will never, I mean, this is the truth. This is how the world sees the thing. In the universe, or if you believe in a higher power, that's how it would see the world. But you don't see this. What you do see is this. You see red samples and blue samples. Can you go from here to here? That's the question. So can you find that rectangle with only finite number of samples? So that is the question. And the next question would be, how many samples would you need to get this right? I mean, do you need 10, 20, 1,000, 1 million, 1 billion? How many would you need? There's a lot of catches here. I mean, what do I mean by right? Okay, and what do you mean by how many? So a lot of these questions need clarification, but this is the broad idea. This is the kind of questions that you would informally ask. Can you find that? So here is another example. Okay, so now you assume the data drawn IID once again from some unknown distribution. All positive data lie inside some half space, say this half space, and all negative data lie in the opposite half space. So half space simply means that you draw a line through the plane, and then one side is half space, the other side is other half space, the opposite half space. So this is the assumption. Now once again, you can ask, once again, as a human being, you never really see this. What you see is this. And the question once again is, oh, sorry, it's not a rectangle. Sorry, this is half space. This is the perils of copy pasting. So can you find the half space that with only finite number of samples? So that's the question. And once again, you can ask the question, how many samples would you need to get it right? Okay, so we'll do one more. Here, the thing is, assumption is that all positive data lie inside some polygon. It could be some polygon, and all negative data lie outside it. So this is the assumption. And the question is, once again, you never see this. What you see is this. And can you find that polygon with only finite number of samples, and how many samples would you need? So these are the typical kind of questions that learning theory would try to answer. So you have to make the assumption clear. Without assumption, you can never make sense of what even right is. Even now, it is not clear what right is, but you can at least go ahead to define what correct and right are. So we'll get there. So are the kind of questions clear to everybody? So these are the exact kind of questions that Valiant addressed in his learning theory, a theory of the learnable paper. Instead of it being geometric shapes, it was all Boolean functions. So the assumption was that you have a Boolean vector, and say your class was really generated by a disjunctive normal form with this thing, and can you identify the disjunctive normal form? So those are the kind of questions that he asked, but we can easily just as well generalize it to other domains. Instead of being a Boolean domain, you can have it a continuous domain. It's a two-dimensional domain, and instead of it being something like Boolean formulas, it can be geometrical shapes. The idea remains the same. The phrasing would be different, but visualizing Boolean functions is not something which humans can easily do. Geometrical shapes are much easier, so that's what I'm going to do. Okay, so that's the question. So is the broad setting clear? And once again, this is by no means the only learning theory. This is just, when someone says learning theory and says the prototypical example, this is what they mean. But there are so many papers on learning theory, every one trying to prove the rightness of a different algorithm on a different kind of problem in a different setting. So I can hardly do justice to even 0.0001%. Even I don't know more than 0.0001%. So that's the status. But this is a very typical example for you to be aware of. Okay. So here is some notation junk, so you don't need to worry too much about it, but we'll get back here if you have some questions. Okay. So we'll once again go with figures. So I find that people understand best with figures, and with geometry, that's the advantage. You can show a lot of nice figures. Okay. So this is the true distribution. Once again, you never see the thing on the left side. That only the higher power can see that. But this is the so the red and blue areas have equal masses. That means that say here are actually 9 triangles. That's why I've put like this. So there are 9 squares here, and I'm saying that the blue square has the same mass as the 8 red squares. That means that the blue square is worth 8 times any red square. So that's so that it makes life simpler for us. It can have it different also, but that's the distribution. That means that what am I saying about the data? The data is, first, you just pick either +1 or -1. Either you toss a fair coin and decide either it's +1 or -1. Once you decide it's +1, you generate a sample randomly from this blue square. If you get a -1, you generate a sample from the red outer square. That's what you do, and that's how you are generating the data. And a typical data might look like this. You can't see the blue circles here, but these are blue circles. Okay, inside the square you have blue circles, and outside the square you might have red dots. So that's how you would have a typical data look like. And you can have the ideal classifier, which is say the green square. So the green square simply denotes the positive area of a given classifier. I'm not going to show the negative area. Anything which is not positive is negative. Okay, so the green area is some classifier showing the positive prediction of some classifier. And this is really the best classifier that you can hope for, right? If you can get this classifier, then you are done. That's golden, right? So that has a true risk of 0. What I mean by true risk is basically what percentage of things would it classify correctly. So that's what percentage of the samples would this classifier get correctly. This would get 100% of the samples correctly. Then you would have an empirical risk, which basically means that you decide that based on only the samples. So in this case, it gets the samples also correctly. All samples it gets correctly, so it's not a problem. So we'll see another example, okay? So consider this classifier now. Ideally, you want the green classifier to be within the black square. So that means that this particular classifier has a true risk of 1/16. Why is it 1/16? Because it gets one square completely wrong. And that square has a weight of half times 1/8, it's 1/16. So that's the 1/16 coming from, because this blue square has a weight of 1/2, and every other square has a weight of 1/16. 1/16, 1/16, 1/16, 1/16, 1/16, 1/16, 1/16. You have 8 such squares, all of which have a weight of 1/16, so that totals of 1/2, and the blue square has a weight of 1/2. Here, this particular classifier gets one square completely wrong. This square should have been negative. I'm not drawing it right, but this square should have been negative, but it's actually saying it's positive. So that means that there is a true risk. The true risk is not 0. But as far as the empirical risk is concerned, it is not getting even a single sample wrong. It is getting all the blue samples as correctly, and it is getting all the red samples also correctly. So the empirical risk is 0. So this is to show that empirical risk and true risk are generally close, but could be different. So that's the idea. So is the definition of true risk and empirical risk clear to everybody? Yeah? This is clear. OK. So another example, say you could have this classifier. Here the true risk is actually half. I mean, you get half the things wrong. And the empirical risk is, you can see that it's actually 7 by 17. I'm not sure if it's correct, but it's more or less correct. OK. So that's the idea. So, and this would be the typical kind of class where you can hope to get. You can never get exactly correct. Here is the empirical risk is still 0, but true risk is not 0, but it is close to 0. This is a kind of, I mean, you would be happy with this classifier. You would not, I mean, you would not insist on this classifier, which is perfect, which is true risk of 0. You would be happy with this classifier. So I will clarify what I mean by that later, but this is, okay. So what is the general algorithm that is used? That the algorithm that is used is basically empirical risk minimization, because you only have samples. You never really see the distributions. You only have the samples. And what you can do is, among all the concepts, you choose the one which has the lowest empirical risk. So what do I mean by a concept here? A concept here is simply a rectangle. So I'll try all possible rectangles, and I'll choose the rectangle which has smallest empirical risk. So here you should immediately ask the question. What should be the question that should come to your mind now? You assume that it's a rectangle, but what if the argument is not unique? I mean, here this classifier has 0 risk. So does this square. Sorry, this is not perfectly perfect. So this square also has 0 risk. So you have to have a tie-breaking criterion. So you have to set a tie-break. So one tie-breaking criterion you could set is choose the largest such square which has 0 risk. I mean, largest such a rectangle which has 0 risk. This tie-breaking criterion is arbitrary. I mean, because there is no way for you to distinguish between two rectangles, both of which have empirical risk of 0. I mean, there is no reason for you to prefer one rectangle over the other, because both of them are performing 100% accurately. There is no reason for you to prefer one over the other. But you have to, for you to return, you can't return multiple classifiers. You have to return a single classifier. That means that you have to have some tie-breaking criterion. So for this purposes of this lecture, we're going to return the largest such rectangle. Okay, so that's the idea. So how would that look like? So for example, for this data, this is how it would look like. I mean, you will find the largest rectangle, which would enclose all the blue things, but would not even contain a single red dot. This is how your thing would look like. Is this clear to you? I mean, can you see why this is the case? Yeah? So now say, assume you have one more sample here, which is a red dot. Now here you have a red dot. Now what would the empirical risk minimizer be? Yeah, so you have to make the rectangle smaller, and this would be the empirical risk minimizer. So similarly, say maybe the next iteration, you have another sample here, in which case the empirical risk minimizer would not be this, but rather this. So every time, I'll go back again. So the empirical risk is going to be 0, but the true risk is, say, I mean, don't mind too much about the number here, the true risk number here. It's not too much of an issue. Just see how it goes. It generally reduces. That's what you'll see. So once you have this, then this becomes smaller. The true risk becomes smaller. The empirical risk becomes 0 again. And then you have another new red point. This particular classifier has empirical risk of non-zero empirical risk, but you can reduce it to a 0 empirical risk. Now the true risk keeps on getting smaller, which is nice, but there is no sequence here. I mean, just imagine every time it's from scratch. Every time you see this data set, you want to find the largest rectangle, which covers the blue points, but does not cover even a single red point. Okay? The assumption was that there exists such a rectangle. That was the assumption, right? So that will never run into an issue where something like this. You would have a red point here, red point here, red point here, and a blue point here. You would never run into such a situation because you made an assumption that there exists a rectangle. So it's a valid. This is not a vacuous statement. You will not have. I mean, this is still valid even if there is such a thing. This is because there's an argmin. But you can actually say that at every iteration you can get an empirical risk of 0. That's actually possible. Okay. So similarly, if you have this sample, then you can have a smaller rectangle. Okay. So if you have finally a sample here, and then you would have this. Okay. So there is hope that, it seems to suggest that if you have enough samples, you will get a classifier which is close to the right answer, right? That means that this looks like a hopeful case. This looks like if you have enough samples, you can do that. So this looks like a case where with finite samples, you can get the right answer. But the right is, again, can you get the exact rectangle here? As the number of samples increases, you have reason to hope that your classifier is going to get better and better. But you will never be able to guarantee that you are going to get the exact square. So that's going to be a hard thing. So you have to relax the right somehow. So that's something we'll get to later. So that's the idea. Okay. Yeah.
What will happen is there is one view dot outside.
It's-
Will it try to cover?
Yeah, so this algorithm is defined even in then. So you are saying that what if there is a blue dot here? Okay, so what is a blue dot here? Even then, it will try all possible rectangles, and it will just find the thing which has a minimum risk, but that it will no longer be 0. There will no longer be a rectangle which has an empirical risk of 0. Every rectangle will have some empirical risk. But that's why I've made a simplifying assumption that that is not the case. The data is always such that there exists a rectangle which will cover your blue samples. You are right that it is generalizable. The result is generalizable to other case also, but for simplicity, we'll assume that there exists such a thing. So that's the key object here is basically the set of concepts. That's basically the set of squares, or the set of half spaces, or the set of convex polygons. So that is basically the main object. Finally, the question will turn out to be, can I learn the set of squares? Can I learn the set of rectangles? Can I learn the set of half spaces? Can I learn the set of convex polygons? So these are the kind of questions that you will finally be able to answer. In the Boolean case, the question would be, can I learn the set of Boolean disjunctions? Can I learn the set of Boolean conjunctions? That would be the set. That's the question that we'll ideally try to answer later on, okay? It's fine. So here the question is, can we ensure the risk is always 0? Can we ensure that? The empirical risk, we can ensure that it is always 0. But the true risk, can we ensure that it is always 0? Generally, no, it is not possible. But we can try to ensure that it is close to 0. That we can try to ensure. But the next question is, can we ensure that we always succeed? What do I mean by that? So the data is random, right? I showed you a typical example of how the data would look like. So I showed you a typical example of how the data would look like. But it is just as possible, not just as possible, it is possible that you have 100 samples, and all 100 samples are the same blue point, right? You have 100 samples, and all 100 of them are this same blue point, over and over and over and over and over. It is possible, because it's probability, right? So it is possible that you take 100 samples, and instead of this nice spread out thing that you get all the 100 samples are close to that same blue point. If that is the case, can you learn anything? If you get 100 samples and all of them are at that blue point, is there any hope of you learning anything? No. There is no real hope of you learning anything. But what we can say is that's a very, very rare event. If I have a distribution over that, I've said it's uniform, right? So why would that happen? That's a very rare. It can happen. No one's saying that it cannot happen, but it's a very rare event. So that is the paradigm that we'll work in. So look at the word here. That's probably approximately correct. So there's 2 levels of hedging there. Right, I said, can I get the right answer? The right requires 2 levels of hedging. One is the approximately part, which is that you can never really get the exact square. That would require infinite samples. With finite samples, you can never really get the exact square. But even with even if you are approximate, so even that you cannot guarantee. It is possible that your training sample is really bad, that you get all the same sample. That is possible, but it is unlikely. It is improbable. It is possible, but improbable. So the only kind of guarantee that you can give is probably approximately correct. So that's the probability here comes from the sample. So the training sample can be really bad, but that's unlikely. So you can say probably approximately correct. So how would the guarantee look like? The guarantee would look like something like this. You have your HS is the classifier that you return. The empirical risk minimization algorithm returns the classifier HS, which is, it takes in your training sample S and returns a classifier HS. the guarantees that you can possibly give are basically something like this. Your risk of your classifier HS is less than or equal to epsilon. Now, the epsilon depends on two things, which is T and delta. What is T? T is the number of samples. And delta is basically the hedge statement. You can't say with 100% surely you will get that, but 99% sure you can say that. So it's the delta is it's saying that it's kind of bounding the bad sample. I mean, only with delta probability you'll get a really, really bad training sample. Which is one example of a really bad training sample is all of them giving the same blue point. If that's the case, it's a really bad training sample. You can't do anything about it. So, but that's an event that happens with delta probability, and delta you can bound. So these are the kind of results that you can actually get. That's basically the risk of your return classifier is less than or equal to epsilon, and that epsilon depends on T and delta. Okay.